So our next talk will be delivered by Ricky Osteen, remotely, and it will be about Jdaviz, an interactive visual data analysis tool for JWST in the Jupyter platform.
So as you just said, I will be presenting a demo of Jdaviz, an interactive visual data analysis tool for JWST in the Jupyter platform, to repeat what you just said. Let me share my screen here, just a moment. All right, hopefully you all can see that lovely opening slide. Now, to repeat myself again, just real quick, Jdaviz stands for James Webb Data Analysis and Visualization. This is a tool being developed by the Data Analysis Tools branch at the Space Telescope Science Institute in Baltimore, Maryland. And we are funded for developing this by the JWST project. So our primary mandate here is supporting the data analysis scenarios that are needed for James Webb, and keeping up to date with the pipeline development and ensuring that we can load and handle the data that will be coming out of James Webb. Now that said, we've been building this to be very general and support data from all sorts of different missions and instruments. And in fact, most of the data you'll see in this demonstration is not JWST simulated data. It's data from other missions. And so if you want to use this tool for things that are not JWST data, and it bothers you that the J in Jdaviz means JWST, I invite you to pretend that it means Jupyter instead for Jupyter data analysis and visualization. Because as you will see, this is all very bound up with the Jupyter platform. Now, let me get rid of these slides and show you something more interesting, namely the application. So Jdaviz currently consists of 4 different configurations. These are sort of pre-built configurations to help with different modes of analysis, and the names are fairly self-explanatory. There's Specviz, which is for analyzing spectra, CubeViz for data cubes, Imviz for looking at images, and Mosviz for multi-object spectroscopy. The first one I will show you is Specviz, and the main way I'll be showing you how to use this tool is embedded in a Jupyter notebook. So this is my favorite way to use this tool. I think it's the most powerful because as you'll see, the application gets put right into the Jupyter notebook, and you can do more coding in the notebook, and you can also pull things out of the app and put them back into the app as you do analysis. So to initialize the application, first I just import Specviz, my Specviz helper from Jdaviz, and I initialize an instance of that class. And then by calling specviz.app, you will see an application now appears in my notebook. It is empty right now, which is not very interesting. So here I'm just going to grab an SDSS spectrum and use specviz.loadSpectrum, and you'll see the spectrum appear in my application. I'll take a quick aside here from this demonstration of Specviz to talk about other ways to use this. You can also call Jdaviz from the command line. So you can call Jdaviz, tell it which layout you want, and give it a file name. And on the back end, this is using Voila, which is a package to render Jupyter notebooks as browser applications. And this essentially hides from the user that they're in a browser notebook. So if the user doesn't need all of that functionality of having a full-fledged Jupyter notebook, they can just pull this up as a browser app, and that kind of all gets hidden in the background. I mentioned Voila. I'll be trying to weave in, as I demonstrate this, some talk about the backend implementation of this and the packages we use. I'll also provide some links at the end to the repositories of all the packages. This is all built on open source stuff. This is all available on GitHub, all that good jazz. So to go over to Specviz, again, looking at the application, I'll talk a little bit about some of the components of this application we see here. At the top, we have what I'm going to call the app level toolbar with things like tools to import data. This is relating to subsets, which I will talk about more shortly. In Specviz, we have a slider where you can set the redshift, which won't do anything until I add some spectral lines, which I will show momentarily. And then perhaps most importantly, in the top right, we have an expandable tray that has some data analysis plugins in it. So these are things, a lot of this is hooking into like astropy capabilities on the back end for things like model fitting, or line analysis, or smoothing data, doing things like that. And these are pre-built, but we hope, and the dream is that the way that you build these plugins is intuitive enough, or at least easy enough to learn, that users could even contribute their own plugins for their data analysis use cases. Going down to this section of the application, this is what I'm going to call a viewer, which isn't super relevant terminology right now because Specviz only has one viewer. But the other layouts we'll see have multiple viewers, so that will become relevant later. If I click this data button, if I had multiple data sets loaded in, I could choose which are being displayed here. In this toolbar, I have things like panning and zooming. I can reset the zoom. I can zoom on either the X or Y axis independently. I can also always save out a PNG of what is displayed in this plot. So if I open that, drag that over onto the screen I'm actually sharing, you can see this saves out just exactly what is shown in this viewer. We don't claim that these are publication quality. That would be nice, but everyone has a different idea of what exactly they want their plots to look like. So we certainly don't guarantee you can just throw this right in a paper. I'm going to show two of the plugins here in Specviz before I move on to QViz, and I'll talk about them just a little bit. I see a live question. The technology used to lift the app out of the notebook into a separate tab is called Voila. And again, I can provide links to those things in the future. And I hope that you're about to see that this spectrum graph is in fact interactive beyond just plotting, panning and zooming around. So the first thing I'm going to show is this line list plugin. I'll talk a little bit more about how these are coded on the back end and the package we use there when I get to QViz. But for now, I just want to show we have some preset line lists that come with the package. The user could also create some files to define their own line lists, or you can go in and create your own custom lines here. But for now, I'm just going to go into this common stellar lines list. And let's see if I can find them. I in particular want to look at these two oxygen lines, and let's just throw a couple more lines on there for fun. So now you can see overplotted on the spectrum, I have a few spectral lines. And this is where this redshift slider comes in handy. As I move this redshift slider, you can see the lines move as I change the redshift. So if I zoom in here a little bit, it's almost as if I've looked at this data before, and these two lines line up, if I can get it right, fairly well with these two emission features here. Now, obviously, there's only so much fine granularity you can get with this slider. You can also do things through the Jdaviz API and the Specviz helper class, like setting the redshift from the notebook. I'm not going to do that now. You could also do things, for example, if you wanted to normalize this, you could pull this data out into the notebook. You could fit and subtract a continuum and then load that back in. That is useful for things like the line analysis plugin, where some of the things that automatically get calculated there are assuming a normalized spectrum. So if you don't have that, it won't crash on you. You won't get sensible values. The other thing I wanted to show here real quick, let me just go in and get rid of these lines because I don't really care about them now. So this is a good time on the back end. This data is being represented as glue data. So glue is a package for doing data representation in a way that provides some nice things in terms of defining subsets of your data and linking different data sets together. I'll talk about that a little more when I talk about Imviz. But for now, the capability we're going to use that is relevant to that is selecting subsets. So I can select this X-range selector tool and say I wanted to fit this broad emission feature here. I could select a little bit of continuum on either side and select that. And now you can see up here in this menu that I talked about before on the toolbar, there's now a subset 1. I could create another one if I wanted to. I don't want to right now. So I'm just going to select subset 1. And now on the back end, the glue data structures now have this global sense of this subset 1. So if I were to go into the model fitting plugin, for example, I could select my data. And here I could say, I'm only interested in fitting subset 1. So when I go to fit this model, it will only fit within those bounds. I'm going to just select a constant because the background looks pretty constant there, and select a Gaussian and add that. And then I want to tell it, I want to add those two model components together. And then I can click fit. And hopefully we can see it did a pretty decent job of fitting that. I will make that line a little bit bigger so it's more visible to you. So I haven't clicked on this tab yet. This is options for the plotting, just in terms of things like increasing the width of lines, changing colors, things like that. And here you can also see the model has been added to the data. So I can get rid of my actual data and just show the model. You can see it fit pretty well. And we can do things like go down in the notebook and call specviz.fitted models to see these models we have fitted. So we can see exactly this is our result and pull that out into the notebook. We can also do things like get the spectra from the data. And specifically here, I'm going to grab the spectrum for subset 1. And you see this automatically gets translated into a SpecUtils spectrum 1D object. And this has a mask applied to it corresponding to the subset that we've defined. So I hope that shows just a quick taste of getting things in and out of the app and a couple of those plugins. I'm going to move on now and show one of the other layouts. So this is CubeViz. Here I've already started the application and loaded some data. So this is a manga data cube. And you'll see here things look a little different from Specviz. So here we have 3 image viewers, and then we have a spectrum viewer. This spectrum viewer in CubeViz and also in Mosviz is essentially just Specviz dropped right into this CubeViz. So everything you saw in the Specviz demo also applies here. I could add spectral lines and things. The only thing I don't have is, instead of a redshift slider up here, instead I have a slider to slice through this cube. And on the image viewers, I could also do things like change the scaling to make things look a little bit nicer. I can change to a different color map, all sorts of great stuff like that. This is probably a good place to mention. So glue is the data on the back end. And then in order to link up the glue data on the back end with this, this front end, which is built on ipyWidgets largely. So ipyWidgets is providing things like sliders and all that nice stuff. There are also some in-between packages called glue-jupyter and glue-astronomy. So glue-jupyter is just connecting glue data structures on the back end with this whole framework in the Jupyter notebook. And glue-astronomy provides some astronomical data specific translators to go between things like the SpecUtils Spectrum 1D object I showed in Specviz and the backend glue data. As a part of all of this, glue-jupyter has 2 plotting backends that are available. So one is matplotlib, which probably most of you are very familiar with matplotlib. But we actually use the other one, which is called bqplot. I believe BQ is because it was initially developed by Bloomberg. So it's probably Bloomberg quantity plots, something like that. Doesn't matter. The moral of the story, this is bqplot on the back end, and that is handling things like the browser canvas rendering in JavaScript and all of that, and exposing in Python a lot of plotting classes for things like the 1D profile plots, the image plots, tables, and we subclass those to provide a little bit of extra functionality specific to us. And I'm sure there will be questions about why did we pick that instead of matplotlib, which astronomers know and love. That decision was before my time, but I am sure that at least part of it is that some of the contractors who work with us are some of the main developers on bqplot. And same with glue-jupyter and glue-astronomy. So we have a very direct line to, if we need things or if we need features that aren't there yet or are buggy in the underlying packages, we have a very direct line for a lot of that to the people who develop those, which is, as you might imagine, a very big advantage for when you're developing an app like this. So let's see, what else did I want to talk about in CubeViz? I thought this would be a nice time to talk about yet another backend package. So I'm going to open this collapse plugin. I'm not actually going to use it right now. Just to note, you can use this to collapse your cubes along whatever axis you want, and perhaps selecting a spectral subset. But I mainly just want to look at this and show how we build this plugin. So we've got some descriptive text. We have a link to the documentation. You can select data. There's a button to actually apply this to your data once you have everything set up. I'm going to go over to the code here. So the way we lay all this out, and I find this very nice because I am not a front-end coder, but we use the Vue.js and Vuetify.js framework package, what have you, on the back end. And there is a Python package called ipyveutify, which allows us to use this easily in Python. And this does some very nice things that I will show here. So the concept I'm showing here, this is a Vuetify template file. So this is defining what this plugin looks like on the front end, the user, what they're going to see. So this is called collapse.view, is just the name of the file. You can see there's things in here, we're defining rows and columns. This vselect is a drop-down menu. So this is hooking into the data items that are available in the backend and keeping track of which you have actually selected. And these, and the other thing I'll mention in a moment, these are actually variables in the Python file that corresponds with this template file. So I'm specifically, going to talk about that apply button. So if I scroll down here, we wrap this in our custom little tooltip class. So when you hover over the button, there's an informative tooltip that tells you what it does. And then there's a V button. This is just a Vuetify button class with our accent color, which is orange. The text is apply for the button. And the important thing here that I wanted to show is that this @click behavior, so this is what happens when we click the button, this just is labeled collapse, which is not super informative, except that in our collapse.py file, what happens is, so our class for our collapse plugin, subclass is this template mixin, and it loads that collapse.view template file. And what ipyveutify does is it connects these two files, and any variable, any method that is named in the Vuetify template file. So for example, that collapse method that happens when you click the button, in the Python file, it knows to look for something called view_collapse. So in the Python file, anything named view underscore what have you is, that corresponds with something in the Vuetify template file that is corresponding to an event or something displayed on the front end. So when I click that button, it knows to go to view collapse and execute all of this code in the Python file. And it's very easy to link things between the back end and the front end. Now, hopefully I can actually get out of this full screen view. There we go, great. And let's see, I have about 7 more minutes left to leave a little time for questions. So I'm gonna move on with our whirlwind tour here to the other configurations, just so I have a chance to show those. So I will move on to Imviz. Here, you can see by default, I have one image viewer. Now, I said that in QViz, the spectrum viewer is basically a full-fledged Specviz dropped into QViz. The image viewers in QViz and Mosviz are not yet fully fledged Imvizes dropped in there in the same way. That's something we're kind of moving towards, but Imviz is a little more different and complex than the other configurations, so it's a little more difficult. And part of that is that we are trying to make Imviz sort of fully featured in comparison to things like DS9, and making sure we get the functionality that you would expect into this configuration. And it's a little hard to get all of that into the other configurations without overloading things. Now let's see. First of all, I'm going to say I have 2 images loaded here. These are Hubble ACS images, I believe. And I'm going to make them slightly more exciting to look at. You may have seen nothing changed there, and that's because in this layer tab, I had the one that's on the bottom selected, and it's covered up by the other. So there we go. That's a little more interesting. So this is intended to be nice for looking at images, doing quick look stuff, and comparing images. So you can see as I move my cursor around, up on the toolbar, if I take my cursor off the image, it goes away. But up on the toolbar, you can see the pixel coordinates, the value there, and the world coordinates as well. In addition to this, I can press the B key and blink between these 2 images. And you can see here, this is where I'm going to talk a little bit about the glue data linking on the back end. These images are currently linked by pixel, and there is some distortion, dithering, what have you going on. So as I blink between them, you can see they don't line up exactly. If I want them to line up exactly, luckily, I can go into the plugin tab, and the only current plugin for Imviz is this links control. So I can instead change from pixels, which is sort of the default for performance reasons. I can change that to a WCS link and either do a fast approximation or something more exact. Fast approximation is pretty darn good. And I can click link, and that recreates the glue links between these two images on the back end to correspond to the world coordinates. So now if I blink between the two images, you can see all of the stars are perfectly lined up because we have linked by world coordinates instead of pixels. Also in Imviz, I can add more viewers. So if I want to view these side by side instead of at the same time in the same viewer, I can do that. And I'm just going to have to change the stretch again real quick. So you can see here, now they're side by side. And if I want to pan and zoom both of them at the same time, I can select this linked panning and zooming tool. And now, as I do things like pan and zoom around one, you can see the other one stays in sync. And that's all enabled by that glue linking on the back end and the way we're representing the data and the fact that this knows that these share a WCS solution, which is rather nice, I think. If there's anything else here, right. We can also select regions. So if I wanted to tell the application I was interested in that star, you can see that region also gets duplicated on the other image because, again, they're linked by WCS. And there are lots of other tools here. You can use the mouse to adjust contrast and bias. I'm very bad at it, so I'm not going to show that right now. Again, you can save out images. You can blink from this toolbar, although it tells you there's nothing to blink right now because I'm showing them separately, not in the same viewer. Yes, that is just a quick demo of Imviz. Let me move on to Mosviz before we are out of time. So this is for doing multi-object spectroscopy. And this is the one place in the demo. This is actually a simulated nearest data set from James Webb. So you can see here, I have an image viewer. I have the 2D spectrum, which will be a little more obvious if I rescale this, that it is a 2D spectrum. There we go. So you can see that's a 2D spectrum. I have the collapsed 1D spectrum, and then I have a table of my sources that I can page through. So here I have about 40 sources. I will note we've done a lot of work recently on increasing performance here. Previously, I think this data set took like 10 minutes to run, and as of now, or to load, 10 minutes to load into the app. Now it takes about 8 to 10 seconds, which is obviously much better. It was painful before. So kudos to everyone on my team who worked on that. And here I can click around the table, and you can see when I click the table rows, that data gets loaded into the viewers. I could also, so I don't have to change the scaling every time. I can click this button up in the toolbar to lock those display parameters. So as I click around, this actually stays useful. A couple other things I will note is that for this nearest data set, all of these objects are actually on one very large image. And so as I'm clicking around on the table, it's actually based on the world coordinates, are in deck in the table here. It's actually zooming on this large image to each individual object. So you don't have to find them yourselves. But if you want more context, you can always zoom out. And I think the last thing I will highlight here in Mosviz before I am done is that, again, because of the linking in Glue, if I pan and zoom along the x-axis of this 1D spectrum, it knows that these share that wavelength axis and it keeps them linked up. So I've hit 25 minutes. I think I will stop there in case there are questions. And thank you so much for listening to my talk. And actually, before I end, let me just show real quick. I do have a slide calling out that we have had just a ton of people contributing to this. This isn't even the complete list. I think I got everyone who's contributed code, but there are many more people who have tested this feedback. And I also have a slide with the links to these packages that I mentioned. I can post this after the talk in Discord. So thank you very much.
Well, thank you. Thanks, Ricky, for this very engaging demonstration and for the impressive tools that you've been developing. I see some typing on the live questions, although that has not come to fruition as yet. Perhaps I'll ask a question which you might have discussed during the demonstration. But are there ways, I mean, to query existing archives, I mean, for your favorite objects, I mean, directly through Jdaviz, or do you need to provide them, I mean, with existing FITS files in order for them to run? Can you actually query archives and download them on the fly?
That's a great question. So from within Jdaviz, there's not a way to query the archives. So you have to bring your data to Jdaviz. However, and I can't believe I forgot to mention this. So I mentioned running it in a notebook. I mentioned running it as a browser app. What I forgot to mention is that in the MAST archives, I'll actually share my screen again here real quick. So the MAST team at Space Telescope is working on integrating this directly into MAST. So while you can't query Jdaviz, you can't query archives from Jdaviz, from MAST, you will be able to open up data straight from the search tab. The intent is you'll be able to open that in your browser in a Jdaviz instance. So the intent eventually is that if the data from your search in the MAST archive is compatible with one of the Jdaviz configurations, you'll be able to click a button right here and it'll open that new data in a new tab and load it for you right into Jdaviz. And lots of people at this conference have talked about the fact that we're going to have just absurd amounts of data from these new missions and how to get the analysis up near the data instead of PIs needing to download the data themselves and do it locally. So this is kind of part of that intent, is that that analysis could be done up on the cloud next to the data instead of having to download everything yourself.
Yes, I can very well imagine that will be incredibly handy to a lot of people, well, even just using, I mean, the huge legacy of Hubble at this stage. Thanks. Now we do have a couple of questions on the live questions channel. So perhaps you can, pardon me? Sure. Michelle can ask it live, I suppose, if she's around.
All right.
Thanks very much for the, where do I look? Oh, there. Thanks very much for the really great talk. This looks pretty cool. I guess the advantage of embedding visualization inside a Jupyter Notebook is that you can obviously do some stuff before you visualize data and then do some stuff afterwards. So I was just wondering kind of how easy is it to actually extract things from the visualization? And the one example I thought of is like selecting regions in an image, for instance, and exporting that to a data frame or doing something with it.
We're trying to make it very easy. So I showed a little bit in Specviz of that, in that you can always call specviz get spectra, and it will output everything as Spectrum 1D objects. And as part of that, if there were subsets defined, it will apply mask to that automatically. You can also always, there's an app level API method that I didn't show called get data from viewer and get subsets from viewer. So if you're only interested in the subset definitions, you could get those out. And I think we may translate those to astropy regions, or we can, or leave them as glue subsets. There's no option to get things out automatically as pandas data frames, but you could do that in the notebook after you got the data out. And then the load data methods into the application, you can pull things out, do things with them, and then load them right back in, is intended to be very easy.
Cool, thanks.
Thank you for the question.
Right. There's now a number of follow-up questions, and I'll ask them in the order they were asked. So Mark Taylor is asking, how performant scalable is Jdaviz for dealing with large data sets, e.g. large images?
It's hopefully okay. Large data sets means something different to some people than it might to me. So I got very scared when I heard the phrase 350 gigabyte PITS file mentioned earlier in the conference. So I can't make any guarantees or estimates how performant it would be with an image that large. I think the images I was showing are around 150 or 200 megabytes, maybe. So we haven't done stress testing on the level of some of these next generation missions that are going to be happening, but we have been doing our best to make things performant. I don't know if that's a Weasley answer or not, but that's my answer.
Yeah, I suggest that along with the several other questions, I mean, you take this up on the specific channel, I mean, for the questions after the end of the talk. But let's thank Ricky for his talk.